Welcome to the deep dive. Today we're getting into something you see everywhere but maybe don't think much about. The humble brick.
That's right. And it's not just any block. We're talking about a material so fundamental, we humans produce over 1 trillion bricks globally every single year.
1 trillion! That number is just staggering.
It really is.
So our mission today is to explore how simple clay, basically baked earth, gets turned into this incredibly durable stuff that keeps our houses standing for, well, centuries.
And believe me, the process is way more intricate and, frankly, fascinating than you'd probably guess.
Okay, so where do we start? Way back.
Let's jump back, say, 10,000 years. We're in Mesopotamia around 8,000 BCE. People wanted sturdier homes than, flimsy huts.
Right. What was the first step?
Pretty basic, really. They started forming blocks of clay, maybe using simple molds, and just left them out to dry in the sun. Sun-dried blocks.
Makes sense. But I imagine they had a major weakness.
Oh, absolutely. Rain, get a decent downpour, and your walls start, well, melting back into mud. Not ideal.
So something had to change.
Exactly. And the game changer, the really decisive factor, was fire. Someone, somewhere, figured out that if you baked these clay blocks, they became incredibly hard.
And crucially,
water resistant. That discovery basically kicked off architectural history as we know it.
Okay, fast forward a bit. The Romans, they were famous for building, weren't they?
Absolutely masters of it. And what's interesting is while the Egyptians were wrestling with these enormous, unique stone blocks, a huge logistical challenge, the Romans were all about the brick.
How so? Did they just make better bricks?
It wasn't just better bricks, though they did improve firing. Their real genius was in mass production and, critically, standardization.
Standardization?
Yeah, they built these huge kilns capable of firing hundreds, maybe thousands of bricks at once. But more importantly, they settled on standard shapes and sizes.
Ah, so every brick was interchangeable.
Precisely. You could rely on them fitting together perfectly. It was essentially the world's first industrialized building material assembly line. That systematic approach, that was the revolution.
That really set the stage, didn't it?
It did. Then you track it through the Middle Ages, bricks become a bit of a luxury item sometimes.
Right, for castles and important buildings.
Exactly. Until the 19th century, when mechanization really took over.
What changed then?
Things like brick presses, machines that could churn out thousands of perfectly formed bricks a day, and continuous firing kilns, like the Hoffman kiln.
So production just exploded.
Completely. It wasn't just large scale, it was continuous, relentless. That's what made the brick the affordable go-to building block for the modern world.
Okay, history lesson absorbed. So let's dive into that modern process. How do we go from digging clay out of a pit to, say, 1 million identical bricks ready to build with?
Well, the whole journey starts deep underground in clay mines or quarries.
But you can't just use any old dirt, right?
Definitely not. Factories are actually very picky. They need specific types of clay ones that are plastic enough to shape easily, but also have the right minerals to fire properly without, cracking or warping.
So they find the right spot, dig it up, then what? Straight to the factory.
Not quite. And this is one of those surprising kind of old school steps that's still vital. It's called weathering, sometimes teguia.
Weathering? What does that involve?
It means leaving the excavated clay outside, piled up, exposed to the elements, rain, wind, frost for weeks, sometimes months.
Months. That sounds incredibly slow. In today's world, why deliberately add that delay? Seems inefficient.
It does seem counterintuitive, doesn't it? But it's crucial for quality. See, that natural weathering process helps break down some of the complex minerals in the clay.
How does that help?
It makes the clay more uniform, more homogeneous, and much more pliable or plastic. If you skip this, you risk ending up with inconsistencies in the mix.
Which could cause problems later.
Big problems. Internal stresses during drying or firing, leading to cracks. Maybe not immediately, but potentially years down the line in the finished building. So this slow weathering is like an insurance policy for long-term durability.
Okay, so patience pays off. Once it's properly weathered, then it goes into the factory.
Then it's ready for processing. First step, crushing. Huge roller mills grind the clay down into very fine, consistent particles.
Like making flour, but with clay.
Sort of, yeah. And while it's being crushed, it's also mixed. Water is added, obviously, to get the right plasticity.
And other things, too.
Often, yes. Additives like sand are mixed in to help control shrinkage when it dries and fires. Sometimes even things like sawdust or coal ash are added.
Sawdust? Why?
When the brick is fired, the sawdust burns away, leaving tiny voids or pores inside the brick. This can make the brick lighter and improve its insulation properties. The goal is always that perfect, smooth, consistent clay mass.
Got it. So now we have this perfectly prepared, pliable clay. How does it become a brick shape?
This is where the heavy machinery kicks in. Typically an extrusion press.
Extrusion, like squeezing toothpaste.
Exactly like that, but on a massive scale. The machine forces the clay mixture through a die, basically a precisely shaped rectangular opening. It comes out as one long, continuous column of clay.
And then chopped up.
Right. An automated cutting machine, usually using wires, slices that column into individual uniform blocks. Super fast, super precise.
And this is where they can add textures or make hollow bricks.
Yes, the die shape determines the final form. If you want textured surfaces, the die can impart that. For hollow bricks, the die has cores that create those internal channels or perforations as the clay is pushed through.
Those hollow bricks are pretty common now, aren't they? Why the holes?
Several reasons. They're lighter, which makes them easier to handle and reduces the load on the building structure. But the main benefit is thermal insulation.
Air pockets.
Exactly. Trapped air is a really poor conductor of heat. So those air channels significantly slow down heat transfer through the wall. Keeps the building warmer in winter, cooler in summer. Saves energy, saves money.
Makes sense. So shaped, cut, maybe hollowed out, ready for the kiln?
Not quite yet. These green bricks, as they're called, still contain a lot of water, maybe 15, even 20% by weight.
And if you put that wet brick straight into a super hot kiln?
Boom. Well, maybe not a huge explosion, but the water turns to steam so fast it would definitely crack or shatter the brick. You'd ruin it.
So you need to dry them first. Gently.
Very gently. They go into controlled drying rooms or tunnels. Over 1 or 2 days, the temperatures gradually increased, maybe from around 100 degrees Celsius up to 400.
Why so slow and controlled?
To allow the moisture to escape evenly from the core outwards, without building up internal pressure or causing shrinkage cracks. It's all about avoiding stress in the material.
Okay, now they're dry. Time for the main event.
Now comes the real transformation. The firing. This is where the magic happens. In massive kilns heated up to extreme temperatures, often between 900 and 1200 degrees Celsius.
1200 degrees? What's actually happening to the clay at that heat?
Chemically and physically, everything changes. At those temperatures, you get processes called sintering and vitrification. Essentially, the mineral particles in the clay start to fuse together.
Fuse. Like melting.
Partially, yes. Some components melt slightly, forming a kind of glassy bond between the more heat-resistant particles. This creates a strong, permanent internal structure. Think of it like creating a ceramic skeleton inside the brick.
And that's what makes it hard and durable.
That's exactly right. It locks in the hardness, makes the brick much less porous so it doesn't absorb much water, and it also determines the final color.
Ah, the color, so that classic brick red.
It comes from iron oxides in the clay reacting during firing. Different clays with different mineral contents fired at different temperatures or atmospheres in the kiln will produce different colors. Buffs, yellows, browns, grays, even blues or purples.
It's incredible that we're basically recreating geological processes, like inside a volcano, just to build walls. No wonder it takes so much energy.
It really does. And speaking of kilns, in modern industry, you mainly see 2 types. The workhorse is the tunnel kiln.
Tunnel kiln.
Yeah, it's a long tunnel, very hot in the middle, cooler at the ends. The bricks are loaded onto carts and move slowly, continuously through these different temperature zones. Very efficient for mass production, very consistent results.
That sounds like the standard for most bricks we see. What's the other type?
The periodic kiln. Think of it more like a batch oven. You load it up with bricks, seal it, heat it up to the required temperature, hold it there, and then cool it all down again before unloading.
Why use that if the tunnel kiln is more efficient?
Control. Periodic kilns are often used for smaller batches, specialized bricks, maybe unique colors or architectural bricks, where you need really precise control over the firing cycle. Less energy efficient, sure, but better for custom work or historical reproductions.
So after hours in that intense heat, they come out finished.
Almost. They need to cool down, and just like the drying, this has to be done slowly and gradually. Cooling too fast can create internal stresses and, again, lead to cracks.
Patience seems to be a theme here.
It really is key to quality brickmaking. Once they're cool enough to handle, then comes the final quality control.
What are they looking for?
Experienced inspectors check for things like uniform color, the right dimensions within tight tolerances, and any signs of defects like cracks or chips. The best ones get packaged, usually shrink-wrapped on pallets, ready for shipping.
And the ones that don't make the cut?
Defective bricks aren't usually wasted. They might be crushed and recycled back into the raw clay mix, or perhaps used for less demanding applications, like fill material.
So there you have it, an incredibly precise, energy-intensive, multi-day industrial process just to make a block.
A very sophisticated block, meticulously engineered from start to finish.
And that standard process is just the beginning, isn't it? Because once they perfect that basic block, manufacturers start tweaking it to create all sorts of specialized versions.
Oh, absolutely. The story definitely doesn't end with the classic, solid red brick. There's a huge diversity out there, each type engineered for a specific job.
Okay, let's talk types. What are the main workhorses?
Well, you have your classic solid brick. Dense, strong, great for load-bearing walls, foundations, anywhere you need maximum stability. Good thermal mass, too.
And we already touched on the basic hollow brick for lighter weight and better insulation.
Right, but then you can get even smarter with the insulation. Take the vertically perforated brick.
Also hollow, but the holes run top to bottom. Why is that specific arrangement better?
It's clever fluid dynamics, basically. Heat tends to want to travel horizontally through a wall, from the warm inside to the cold outside.
Okay.
By arranging the air chambers vertically, you force the heat path to cross multiple layers of trapped air. It creates a much longer, more convoluted path for the heat to escape.
Ah, like a maze for heat.
Exactly. It significantly increases the thermal resistance, what we call the R value of the wall. That's why these types are crucial for meeting modern energy efficiency codes in buildings. They save a lot on heating and cooling bills.
Okay, smart design. What about bricks built for toughness, for extreme conditions?
For sheer longevity and battling the elements, you want clinker brick.
Clinker. Sounds tough.
It is. These are fired at even higher temperatures than standard bricks. This makes them incredibly dense, very hard, and almost completely non-porous,
Meaning?
meaning they absorb virtually no water. They're highly resistant to frost damage, chemical attack, abrasion, everything. A facade made of clinker brick can last for centuries with almost zero maintenance. You see them a lot on older, very durable buildings, especially in Northern Europe.
Wow. Built to last, literally. What about looks? Any bricks designed for style?
Definitely. That's where glazed bricks come in. They have a special ceramic coating fused onto the surface during a second firing.
Like pottery glazing.
Pretty much the same idea. This glaze gives them a smooth, often shiny, and sometimes brightly colored finish. It also makes them impervious to water and dirt, so they're easy to clean. Very popular for decorative accents, unique modern facades, or places like subway stations.
Makes sense. And any for really specialized industrial uses?
Oh, yes. Think about lining a blast furnace or a large industrial chimney. You need something that can handle incredible heat.
Right. Ordinary brick would melt.
Or crumble. That's where fire-resistant bricks or refractory bricks come in. They're made from special clays with high alumina content and can withstand temperatures up to 1,500 degrees Celsius, sometimes even higher, essential for any high-temperature industrial process.
We mentioned sustainability earlier. Are there bricks specifically designed with the environment in mind? We talked about the air-dried mud brick revival.
Yes, the unfired mud brick is a great example of low-impact building, especially in the right climate. Its ability to breathe and regulate humidity naturally is a huge plus for comfort and reduces the need for artificial air conditioning.
And beyond that?
Well, the vertically perforated bricks we discussed are key for energy saving. But there are even more specialized types emerging, things like sound-insulating bricks designed to combat noise pollution in cities.
Interesting.
Or even water-absorbing bricks, believe it or not. Designed for use in hot, dry regions to capture and retain rainwater or atmospheric moisture, helping to cool buildings passively through evaporation. Really innovative stuff.
That incredible variety really highlights how adaptable the brick is. But that brings us to the future, doesn't it? Sustainability, competition. These seem like major challenges.
They absolutely are. Let's connect this back to climate change. That 1,200-degree firing temperature, it requires a massive amount of energy.
And historically, that energy came from?
Fossil fuels, natural gas, sometimes coal. Burning those fuels releases huge amounts of carbon dioxide. So the brick industry traditionally has had a pretty significant carbon footprint. That's its biggest environmental hurdle right now.
It's a tough problem to solve. But bricks do have that incredible lifespan, right? Does that count for something in the sustainability debate?
It counts for a lot. You're right. A well-built brick structure can easily last hundreds of years. Compare that to, say, some modern concrete structures, which might be designed for a lifespan of maybe 50 or 60 years before major refurbishment or demolition.
So the environmental cost is spread over a much longer time.
Exactly. The embodied energy per year of service can actually be quite low for brick. Plus, at the end of its life, brick is highly recyclable.
How does that work?
Old bricks can be cleaned up and reused whole, especially historic ones. Or, more commonly, they're crushed down. This crushed brick, or aggregate, can be used in roadbeds, for drainage, or even as a component in making new bricks, creating recycled brick.
A circular economy, then?
Potentially, yes. If the industry can tackle that initial energy consumption for firing, brick has strong long-term environmental credentials compared to materials that are harder to reuse or recycle.
And is the industry tackling that energy issue? Are we seeing innovations?
We are, definitely. There's a lot of research and development happening. We already talked about the high insulation types that cut down on heating and cooling energy once the building is in use.
What else?
There are active efforts to fire bricks using cleaner energy sources, things like biogas, hydrogen, or even electricity from renewables, aiming for carbon-neutral production. It's challenging at those temperatures, but progress is being made.
Any other futuristic brick?
Some really interesting concepts are being explored. Bricks designed with special surface structures or catalysts to actively absorb air pollution, like particulate matter, in cities.
Wow, bricks cleaning the air.
Potentially.
Ah.
And then you get into things like 3D printed bricks, using less material maybe, and the really forward-looking stuff, smart bricks.
Smart bricks, what can they do?
Still largely developmental, but imagine bricks with embedded sensors or phase change materials that can store heat, or even integrated thin film solar cells to generate electricity. The brick itself becomes part of the building's functional systems.
That's incredible. But while brick is innovating, it's also facing the serious competition, isn't it?
It really is. Concrete is still often cheaper, and for massive structures like skyscrapers, its compressive strength is hard to beat. You can't really build a super tall tower out of traditional brick.
What about residential?
There, you've got lighter, faster materials gaining ground. Timber frame construction is popular. Sustainable composites are emerging. Speed is a big factor.
And the biggest disruptor, maybe? Modular construction.
That's a huge one. Building entire sections of houses, or even whole houses, in a factory, and then just assembling them on site in days. That completely changes the game.
It cuts down labor time dramatically compared to traditional bricklaying.
Massively. It bypasses weather delays, improves quality control potentially. It's a direct challenge to the slow, methodical pace of traditional brick construction.
So, with the carbon issue and all this competition, what's the verdict? Is the brick's dominance coming to an end?
Look, it's complex. I don't think brick is going to disappear entirely. Its core strengths, durability, thermal mass, fire resistance, that feeling of solidity are still highly valued.
Right.
But the industry has to evolve, and rapidly. It needs to solve that energy and carbon problem, maybe integrate more technology, perhaps find ways to speed up construction. It has to become greener and smarter without losing what makes it brick. It's a real balancing act.
What a journey it's been from, those first sun-baked blocks turning to mush in the rain to potentially these smart bricks generating power. 10,000 years of adaptation.
It's remarkable, isn't it? If humans have stuck with it this long, constantly reinventing it, you have to assume it's got more transformations left in it.
Maybe in 50 years we'll have self-repairing bricks or ones made entirely from recycled waste. Who knows?
Exactly. It shapes so much of our past. It seems likely it'll keep shaping our future. The big question is, will it still be the dominant player in our cities a century from now? Or will concrete, wood, or some entirely new material finally push it aside? What do you think is its most enduring quality? That resilience from the fire, or just the sheer familiarity and trust we place in it?
Something to think about next time you walk past a brick wall. Thank you for joining us for this deep dive into the surprisingly complex life of the building block.
Thanks for having me.
We'll catch you on the next deep dive.